That was amazing. All right. So, guys, what we're going to do today is I'm going to lay out for you some calendar stuff because it'll be helpful for you to understand how everything we're doing sort of fits together. So we're going to reverse engineer this. You'll see in a second. Then, guys, we're going to grade homework. But when we do, we're actually going to be highlighting some things that you're going to need moving into what we're doing for the next 4 days. So we're not just going to look at questions and answer your questions. We're going to make sure that we're making these connections. And then, guys, after all of that, today's going to be a relatively short day. We're going to gather around one new idea. You'll see how they fit together. And then, guys, at that point, you'll have time to work on homework. Okay, so, guys, the connections go like this. So when we got together last time, which was the first day of the unit, we talked about polarity. We talked about this idea of unequal sharing. We talked about the idea that electrons drift, and when they do, the bonds get unbalanced. You have a negative end and a positive end, and that can lead to polar molecules. So now, guys, this is the progression. Today, we're going to find out that these polar molecules are sticky. Then we're going to find out that these sticky molecules behave differently because of their stickiness. And then, guys, coming back after Martin Luther King weekend, we're then going to go into lab and we're going to look at one of the things that changes based upon stickiness. And guys, that is the phase that these things exist in, solid, liquid, or gas. So we're going to study that. Then, guys, when I see you on Friday, we are actually going to have a video day. We do this every year. We bake it into what we're doing. But, guys, if you're going to be gone, or it's a day that just sort of stands on its own. So we'll talk more about that later. Then, guys, coming back after that weekend, we're going to get into kind of like taking the lab that we did here on Wednesday. And on the next Tuesday, we're going to actually edit it and perfect it and get it all tied together. Then there's one more thing we need to talk about in this unit, and then we're done. But, guys, the important thing right now is this. It's a progression. So we're going to go, molecules are polar, that makes them sticky, that makes them behave differently, and then we're going to study that in lab. Did that make sense? Is that okay? Okay. Then, guys, this. We need to now talk about remediation. So last time in class, you got your test back. If you're in Miss Call's class, you didn't, but we talked. But, guys, this is how this is going to go. So on Tuesday or Wednesday, we're going to do remediation. And, guys, that's going to be on Wednesday right after fourth period. Because remember, it's early out. We don't have flex time, but we're going to do it right after school on Wednesday. And then the essentials test will be on Thursday. We good on calendar stuff? We're all set? Okay. So, guys, grab your homework and let's take a look. Here we go. So get rid of this. Get rid of this. Get rid of this. Grab a hold of this. And let's take a look at them. So, guys, I don't believe I mentioned this to you, and please ask questions as we go. But I don't believe that I mentioned to you that, well, I know that you don't need to know the names and angles, because then why did I put them on the homework? And the answer is because some people find them useful as references. So like when you look at that first molecule and you're like, wait a minute, I don't understand the shape of it. I gave you the names and angles just in case that was helpful for you to come up with the shapes. So guys, how we doing? 1 through 4. There's really nothing here that I wanted to pull out other than this. Were you guys able to think through this? The idea that this bond is polar this way, this one's polar this way, and this one's polar this way. So guys, why is the overall polarity towards the oxygen and not the chlorine? It's stronger. The oxygen is stronger than the chlorine. And so this guy is actually pulling the strongest, and therefore it's polar in that direction. Is that okay? Okay. So then, guys, moving along. You said, are we good 1 through 4? Is that okay? All right. So let's get rid of that. Let's go here. Let's go here. and off we go. We okay here? Clarifications. Guys, remember we're drawing them as three-dimensionally accurate as we can. So the top one there, you see the 120-degree angles, and all of those poles cancel out. Is that sitting okay? Okay. So then, guys, moving along again, we get to this set. The number 8, again, is trigonal planar. And those all cancel out. Number 9 is symmetrical. And then, guys, number 10. Can we talk about number 10? Did any of you struggle with this? So, guys, let's talk about it really quickly. On number 10, many people draw its Lewis dot structure like this. And forgive me for not drawing the extra electrons around the chlorine. But, guys, a lot of people draw this molecule like this. And that's totally fine, but if you did this, did you find the problem? You can't draw the polarity arrow into this. Because, guys, technically the polarity arrow is coming out of the screen, and you don't have a way to draw that. So let me give you a little hint that'll keep you from getting in this situation. Guys, what you got to do is if you have similar atoms in a molecule around the outside, put them as close together as you possibly can. So instead of putting the chlorines across from each other, put them next to each other, and then you'll be able to draw those arrows more easily. Good there? Okay. Then, all right, where are we at? We still have more. So guys, moving then down here. And guys, on some of these, the legs got cut off the hydrogens, like number 13. I don't know why, but... You guys okay on these? You're scaring me. You guys are usually full of questions, which means you either really understand this or I freaked you out because I told you about the fact that we're recording this for other people.
Hi.
Ishmael says hi. Thanks to speech therapy. Probably shouldn't have said that. All right. You guys okay? Are we good? All right, guys, wrapping this up. Here we go, and now we need to slow down, and now we need to talk. So, guys, number 16. We'll get there in a minute, but you're gonna see, guys, that number 16 and number 19 are critical to what we're doing today. Not that the other questions aren't important, but guys, we've got to talk about number 16 and number 19. So I think number 15 probably sat okay. What are dipoles? Things like that. But guys, we really need to do a deep dive into number 16. And the first thing you need to know is I think this is wrong. Did you guys go over that? And so, guys, I believe that number 16 is wrong because there were misprints on my older version of the periodic table. So let's talk about the theory and not get caught up in maybe the mistakes. I'm pretty sure this is not right. But guys, the idea is this. Number 16 said, here's a bunch of bonds. Put these bonds in order in decreasing polarity. So guys, how do you find out the polarity of the bond? And it goes like this. You find the strength of one atom, you find the strength of the other atom, you subtract, and the difference between those tells you the polarity in the bond because it's the difference in the stealing power of the two atoms. So guys, fundamentally, the bond that has the largest difference in electronegativity will be the most polar or the most shifted. And then, guys, the bond that has the lower or the least difference in electronegativity will have the smallest polarity because they share more equally because their strengths are similar. Does that make sense? Is that okay? We good? That's going to be important today. So, guys, that's number 16. Then let's jump down to number 19. And then if you have questions, we can look at those as well. But guys, number 19 is going to make your life a whole lot easier. So guys, number 19, and I know you're looking at the answer, and so we're sort of starting with the end in mind. But guys, number 19 says this. What are the two characteristics that make molecules polar? So guys, let's go through each one of these. Go back up to number 1 and let's look at these. And you already know the answer, but let's talk about these trends. So guys, the answer is this. What makes a molecule polar? It's one of two things. There's either unbonded electrons on the central atom, or the atoms that are around the outside are not the same atom. So guys, let's do this. Number 1, different atoms. Number 2, unbonded electrons. So guys, why is number 1 polar? Is it different atoms or unbonded electrons? Different atoms. So guys, the idea is this. Chlorine is not oxygen. As a result, that will be polar. Now guys, what about this? Why is this thing polar? Different atoms. Hydrogen is not fluorine. So now let's go down and look at number 3. And the idea is this. They are the same atom. But yeah, there are unbonded electrons there. This is the one exception to the rule because there's nothing for those unbonded electrons to bend. So this is the one exception to the rule. So now guys, let's do this. Look at number 4. Why is number 4 polar? Is it different atoms or unbonded electrons? Unbonded electrons. See guys, this is an oxygen and this is an oxygen. Those are the same atoms. The reason that this is polar is because of unbonded electrons. So here's what we're going to do. Different atoms we're going to call number 1. Unbonded electrons we're going to call number 2. So we're just going to go different or unbonded. Different or unbonded. So guys, number 5. Notice there are not different atoms, no unbonded electrons. So guys, that would be nonpolar. What is it then on number 6? Different atoms. Number 7? Unbonded electrons. Number 8, that's nonpolar. Number 9, nonpolar. Number 10, different atoms. You starting to get the idea? Number 11, unbonded electrons. Number 13, different atoms. Number 14, different atoms. And we're done. So guys, that will never fail you. If you have different atoms, it'll be polar. If you have unbonded electrons, it'll be polar. Other than that, it will be nonpolar. Does that sit okay? So guys, in my mind, we're done with the homework. Are you guys all okay? Other questions or things to talk about? So guys, tuck this away, push it off to the side. We are not going to record our homework scores right now, simply because we're going to tighten up this video. And so guys, grab note-taking materials, grab your periodic tables, and today is a relatively straightforward day. Here we go. Get rid of this. Grab a hold of this. All right. So guys, the date today is the 10th. Actually, need some re-stretching. Or are you looking for a really awkward high five? Sure. So guys, the date today is the 10th, and the topic for your notes today is polarity and intermolecular forces. So guys, I know that intermolecular forces is a relatively long clustering of words. For the rest of the year, we're just going to write IMFs. So when you see IMFs, we're talking about intermolecular forces. But guys, when you think about intermolecular forces, if you just think about the word sticky, you're going to be just fine. So when you think intermolecular forces, just think about the idea of stickiness. Because guys, remember that's the progression we looked at on the calendar. We said polar is sticky, sticky behaves differently, and then we're going to do the lab. So guys, when you think about intermolecular forces, just think about stickiness and you'll be good to go. So guys, it goes like this. This is the big idea for today. Do not write any of this down. But guys, this is where we're headed with this. In the coming days, we're going to take these progressions of ideas, and frankly, guys, we're going to be talking about stuff that is going to change the way you look at the world. And I know that that sounds weird, but it's really true. Guys, we're going to be answering some really fundamental questions that you probably don't know the answer to. Like, for example, why does sugar dissolve in water? Because if that seems like a silly question, let me ask the other side of this. Why does sugar not dissolve in gasoline? It's strange, right? You would never put sugar in gasoline. But guys, sugar dissolves in water, but it doesn't dissolve in gasoline. Why not? And then we can even take it to the next level and say, why does gasoline not dissolve in water? Because there's all sorts of interesting relationships we can talk about. We're going to talk about things like this. Why is sugar a solid? Why is water a liquid? And why is carbon dioxide a gas? We're going to talk about the way these things behave. Guys, this one's really interesting. We're going to talk about why does water expand when it freezes? Guys, that's why our pipes break when it gets cold outside. Because did you know this? Water is the only substance on Earth that expands when it freezes. The only substance on Earth that expands when it freezes. So why is water so different? And then, guys, questions that are really practical. Why do we put salt on our roads when they're slick? Interesting stuff, and we're going to dig into all of this. So, guys, interestingly, all of these questions have the same answer, and it all comes down to polarity. So, guys, the idea is this. Last time we learned that, and don't write this down, last time we learned that polar bonds can lead to polar molecules. Guys, we represent these polarities using arrows. And so, guys, the idea is that these molecules, the ones that are polar, either have dots on the central atom or they have different atoms surrounding that central atom. And we talked about that before. So, guys, today what we're going to do is this. We are going to take this conversation next level, and we're not just going to talk about polar, we're going to talk about more polar. And guys, that leads us to question number 16 in the homework, where we were figuring out the polarities of the bonds. So guys, this is what we're doing today. We are going to talk about not just polar, but we're going to talk about more and less polar, and then we're going to tie that to stickiness, which is intermolecular forces. You ready to go? Goes like this. So guys, what we're going to do is, first of all, and this stuff you do want to write down. Guys, we are now going to define these things called IMFs. So in your notes, just write down IMFs and let's define this. So guys, the idea goes like this. Polar molecules, when they're gathered into groups, attract each other. They are sticky. And guys, literally what happens is the positive dipoles attract the negative dipoles, and this creates what are called intermolecular forces. Now guys, inter means in between. And obviously we're talking about forces. So guys, these are forces between molecules. Now guys, there are some things you need to know about these intermolecular forces. First of all, they're weak. Doesn't mean they're not important, but they're not strong. So what do we mean by weak? And guys, the answer is this. They're about 1/10 to 100th the strength of a covalent bond. So between 10% and 1% the strength of a covalent bond. So they're not very strong. They're very important, but they're not very strong. But guys, here's the thing that's interesting. And I'll wait for you to catch up. You guys okay? Yep. You guys okay? So guys, which one is it? Is it 1% or is it 10%? And guys, the answer is it depends. And what does it depend upon? The polarity. And how do we know the polarity? By subtracting electronegativities. So guys, the idea is this. The strength of the intermolecular forces is determined by the polarities of the bonds. And we know from question number 16, we can find those by subtracting electronegativities. And that's how this all comes together. So guys, the more polar the molecule, the stronger the intermolecular force. So guys, once you're caught up to there, you're done taking notes. What we're going to do now is we're going to start drawing Lewis dot structures, and we're going to start talking about not just polar, but we're going to talk about more and less polar. But guys, before we do this, don't write this down, but there's one other thing that you need to know. Guys, when we get deeper into these understandings, we're going to be using the word therefore a lot. This is true, therefore this is true, therefore this is true. But guys, we can avoid writing the word therefore. Did you know there's a mathematical symbol for therefore? Did you know that? It's actually this. These 3 dots are actually the mathematical symbol for therefore. And so guys, when we do these logical arguments, rather than write out the word therefore, we're actually going to use the triple dot to represent therefore. You guys ready to start drawing pictures? Here we go. So guys, what we're going to do is this. We're going to draw the Lewis dot structures for these 3 molecules. Guys, I'm going to give you a couple minutes to do this. Spread them out across your paper. Make them big. The reason that we're making them big is because we're going to be drawing in arrows and polarity arrows and nonpolar, and we're going to dig into these. So guys, on the left, CH4. On the right, water, and in the middle, CH3OH, which, guys, is actually methanol. It's an alcohol. And we're going to draw their Lewis dot structures. So, guys, go ahead and do this. But, guys, please draw them as 3-dimensionally accurately as you can. And so in order to help you with this, let's do this. Do number 1, do CH4 first. Then do water second. And then wait for me for CH3OH. But again, guys, draw them as 3-dimensionally accurately as you possibly can. So guys, let me give you the first one. I'm assuming that you're done with it by now. So guys, CH4 looks like this, right? That's its Lewis dot structure. But guys, just in your brain for a moment, can you picture what this looks like 3-dimensionally? You don't even need to know the name tetrahedral. But 3-dimensionally, guys, it looks like this. And that is the best that we can do. This Lewis dot structure is the best that we can do for drawing tetrahedral. So we're going to leave it like that. You don't need to draw this. You just need the Lewis dot structure. But you need to make that 3-dimensional connection. So guys, now let's go over and let's do water. And water looks like this. But guys, as you were drawing the Lewis dot structure for water, some of you may have put the hydrogens to the left and to the right. And remember what we learned last time. Guys, we don't draw water like that. Is it wrong? No. But guys, it's not best because we understand that water is actually bent. And because water is bent, we're going to draw this molecule bent because it looks like this. So again, guys, we're drawing them as 3-dimensionally accurate as we can. So now, guys, did you pick up on this? CH3OH. Do you see that CH3OH is actually a bringing together of this and of this? So if we take a hydrogen off of this, what do we have? CH3. And if we take a hydrogen off of this, what do we have? OH. And so, guys, that is actually, well, it's kind of how alcohols form. But the idea is if we put these together, we end up with CH3OH. So what we're going to have is we're going to have a part that is tetrahedral, and then we're going to have a part which is bent. And so when we bring those two things together, what we do is we represent them like that. So guys, this is the way that we draw CH3OH. You've got the tetrahedral part over here on the left, and then you've got the bent part over here on the right. So we're going to draw it like that. Hey guys, if you're curious, the molecule actually looks, the molecule actually looks like that. Yeah?
So what happened to what happens to the hydrogen?
That's a great question. They actually leave as H2. Yeah, shoot, there's so much that would be interesting to talk about this. But just let me lay this out there for now. So many times in biology, this is the way molecules form. Is you end up with molecules that have hydrogens. One big molecule here, another one here, you got hydrogens. And the hydrogens fall off, and in the absence of those hydrogens, they bond together and make even bigger molecules. It's even sometimes the way plastics form. They're called polymers, and poly is many. So you end up with atoms like hydrogen falling off and just chains of these molecules forming. Yeah.
Does the hydrogen just is its bond not as strong so it falls off?
I love that you're thinking about why, and that's amazing. And the answer, surprisingly, Aiden, is no. Right? You would think that it's just because this bond is relatively weak and that one's and they fall off and then they bond. It's actually not the case. What you have to do is you have to put the CH4 and the water in an environment where you can weaken those bonds. We do that using other reactants. We can use catalysts, but we have to do something to weaken those bonds before we can get them to bond together. That's actually what enzymes do in our bodies. Yeah, if you've heard of enzymes, they're molecules that weaken bonds that cause other things to stick together. Yeah, that's a really neat question. You guys doing okay with these ideas? All right. Now it's time for you to get to work. Draw in all the polarity arrows. Grab your periodic tables, flip them over on the back. Guys, we're going to do them one at a time. So let's do CH4 first. Draw in all the polarity arrows for the bonds. So, I struggle with the numbers. Is hydrogen like 2.2? Is that true? And oxygen's in the 3s, right?
Yeah.
Okay. So we know that carbon is stronger. Did I say oxygen? Carbon. Sorry. Carbon's not in it. Oh, shoot. This is trickier.
2.5.
So say that again.
Carbon's 2.5, hydrogen's 2.1.
Okay, so carbon's stronger, right? Okay, so guys, what that means is this bond is polar this way, this one's polar this way, this one's polar this way, and this one's polar that way. Are we all settled with that? Okay, so now guys, we need to do the polarities for these other two molecules, but in an effort to make our lives easier, I actually looked up all of these electronegativities and they're on the screen. So hydrogens, wait, on your periodic table, doesn't it say hydrogen's 2.18?
Yeah.
Shoot. I did this last year on an older periodic table and they've adjusted the value. Is carbon still right?
Yeah.
Oxygen? 344?
Yeah.
Okay, so you can go from there. So guys, draw in the polarity arrows for the rest of these dudes. You're going to see in a minute why I did this, but for now, draw in the polarity arrows. Hey guys, I know some of you right now are even taking the logical next step and you're drawing in the polarity arrows for the molecules. That's awesome. We're going to do it together in a minute, but if you're doing it now, that's great. Feel free to talk about it. That is where we're headed. Are we okay to, let me at least do this. Let me draw in the polarity arrows for the bonds, and then we can look at the overall for the molecule. So carbon stronger than hydrogen, carbon stronger than hydrogen. Then guys, the carbon-oxygen bond, that's polar towards the oxygen, right? So this guy is flowing in this direction, and this guy is flowing in that direction. And guys, that would be the polarities of those bonds. Then, moving over to water, we know that those are the polarities of those bonds. So now, guys, let's take the next step and let's draw in the polarity arrows for the molecules. So, guys, looking at CH4 over here on the left, what direction does that polarity arrow go? It don't. It's non-polar. So guys, let's put it to the test. Are there unbonded electrons on the central atom? No. Are all the outside atoms saying, yeah, this is non-polar? So guys, all we do is we come along and we say that this is non-polar. Do that with me. Okay. Now guys, holy smokes. Obviously these things are polar, right? So let's pick the easy fruit first and let's go to water. So guys, water is polar. We know that. We can explain it. There's unbonded electrons on the oxygen. But again, guys, we have a push that's going up and we have a push that's going right. So what is the overall movement? Up and right. It is diagonal to the upper right. Now, guys, methanol. This is alcohol, methanol. It's a mess. So here's what we've got. We've got movement towards the carbon, right? But then we have movement towards the oxygen. So the entire top of this molecule, if you will, is flowing towards the oxygen. But then we've got movement from the bottom flowing up. So what will the sum of all of that movement be? It's going to be up and to the right, but through the oxygen. So that would be the polarity of this molecule. Everything on the left is flowing towards the oxygen. The hydrogen is flowing up towards the oxygen. And that is the overall polarity. So now, guys, you ready for the one new slice and we're going to work on homework? Now we're going to put these in order by increasing polarity. Which one of these is least polar? Which one of these is most polar? And which one of them is in between? So guys, let's do the easy one first. Which one's the least polar? Non-polar. So we're just going to label this least. That is the least polar. But now, guys, I'm going to clean up my mess, and then we're going to talk about more polar. So this molecule is polar in this direction. This molecule is polar in this direction. Now, guys, the question is this. Which one is the most polar? Guys, do you remember? How do we find the polarities of the bonds? Question 16. What do? Subtract electronegativities. So, guys, let's go over and let's do that for water. So 344 minus 2.2 is 1.24. Guys, write this down with me. The polarity of that bond is 1.24. Then the same math, the polarity of this bond is also 1.24. So guys, water contains two polar bonds and their polarities are both 1.24. Is that okay? Now let's go over and let's look at the alcohol. Well, guys, here we have an oxygen and a hydrogen, just like in water. So its polarity is 1.24. But guys, what about the other side? Now we have a carbon bonded to an oxygen. And when we subtract those, 0.89? Why can't I do subtraction? Guys, that's 0.89, right?
Yeah.
Tell me let's pretend it's 0.89. 0.89. Is that really right?
Yeah.
Oh, good. I didn't want to grab my calculator because that would be embarrassing. But, guys, what does this tell us? Well, guys, what this does is it tells us the polarity of the molecules. But we have a question. Obviously, on water, these are the only bonds that we had, and so we found their polarities. But guys, how did we know which bonds to look at over here in CH3OH? And here's the answer. You always look at the bonds that are right next to the polarity arrow. You don't need to worry about these. It's just the bonds that are right next to the polarity arrow. And then, guys, bringing these ideas together, here's how it goes. Water has bonds with more polarity, so this would be the most polar. And then, guys, alcohol, because it has a bond that is less polar, this polarity would be in the middle because it has a bond that is less polar than the two bonds in water. What do you think? So, guys, if this is sitting okay, we now need to ask the therefore question. So what? And guys, what you're going to find out on Friday is there's a lot of really interesting so whats. So what that ethanol, that methanol, alcohol is less polar than water? Guys, who cares? And the answer, and you're going to find out on Friday, is there's a lot of really interesting things that are true just because water is more polar than alcohol. And we're going to look at that stuff on Friday. So guys, this is where we're at. We're done. Questions? Grab your homework packets. Guys, your homework packets look like so. Homework assignment number 2. But guys, you'll notice at the top of this, do you see where it says homework assignment 2 and 3? You're only going to do half of this. It is 3 pages long, but you're only going to do half of it. So guys, I want to step you, actually it's 4 pages, isn't it? Oh, maybe it's just 3. So guys, I want to step you through what you're going to be doing, so join me at the screen. So guys, the first thing you're going to do is this page, but you're only going to do the left and the center column. Guys, the right-hand column is all of the therefores. So what you're going to be doing is the left-hand column, but guys, only the ones where you have information in the left 2 columns. So you can't do number 1 yet because you don't have any information. But guys, now what we need to do is we need to tie these ideas to intermolecular forces. We already now know how to figure out the polarities. We did that just a minute ago, but now we need to tie it to intermolecular forces, and it goes like this. Guys, if you have a molecule with low polarity, that will have low or weak intermolecular forces. Then, guys, you can't do number 3. There's no information. Then looking at number 4. If you have a molecule with strong intermolecular forces, up arrow, that has to be a highly polar molecule. Then, if you have number 5, a high polarity, what has to be true of the intermolecular forces? High or low? High. You get the trends? Guys, high polarities lead to high IMFs, low polarities lead to low MFs. Skip the one where you have no data. Good? I'll take you 12 seconds. So guys, now change pages with me. Come on. Not going to work. Just a second. We'll get it. Boom. Boom, 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 boom. Okay, here. So guys, read the instructions with me for these. Basically, what the instructions are telling you to do right here is do what we did on the previous page. So what you're going to do is you're going to draw the Lewis dot structure side by side for these two molecules. Then you're going to draw in all the polarity arrows and the overall polarity arrow, just like last time in homework. But then, guys, what you're going to do is this. You are going to circle the most polar molecule. Using the strategies that we learned on the previous page, you're going to circle the most polar molecule. And then, guys, when you're done with that page, you're done. We're not going to do, is there a page after or a page before? A page after. We are not going to do that. We will on Friday. So, guys, this is what we're doing for homework today, finishing the arrow things. And then, guys, on that third page, drawing their Lewis dot structures. With that said, one other thing. Guys, when you get down here to these molecules at the bottom, these guys, you should, well, you already have drawn methanol. You can just you can copy it out of your notes. Guys, you're welcome to fiddle around with diethyl ether if you want, but you may just want to look up the structure in the answers to the homework and then draw in your own polarity arrows. And then, guys, acetone and propanol, I would never expect you to be able to draw these on your own. If you don't know, acetone is nail polish, fingernail polish remover. Propanol is another alcohol. But guys, don't try to draw those on your own. Just copy them out of the answers. Then draw in your own arrows, and you still should be able to figure out which one's most polar. So, you have a clear sense of what we're doing? So, guys, remember it's early out today, so we have a little bit shorter time. But really, you should still get this done today. The answers will be up front. Feel free to check as you go. Guys, let's get this knocked out, and that'll do us for the day. We good? Okay.